Okay, let's discuss rotating conics. First things first, what's a conic section? Well, we've already discussed what conic sections were. It's when the shapes that you get when you slice a cone. And then now we're going to talk about how to identify what conic section we have, looking at it in a general form. So a standard form is the conic section form that you're used to seeing. It's where you can pluck out the H and K for the center, and you can pluck out your A and your B and your C, or find your C, right? So that was really nice. But general form is where everything is multiplied all out, as you see here on the screen. So where do we go from here? Excuse me. You will notice that in these 4 types of equations, there's a few things to note. One, none of them have a bxy, so none of them have this term right here. In other words, all of these have a b value that's 0. Okay, so if the b value is 0, we can identify the conic section. If the a and the c, so the coefficient of the x squared and coefficient of the y squared, if they are of the same sign, so they're either both positive or both negative, then we have an ellipse. Okay? If they're straight on equal, we're going to have a circle. If they're of opposite sign, we have a hyperbola. If we have an x squared term but not a y squared term, or we have a y squared term but no x squared term, then we have a parabola. Okay? Oh, just trying to scroll up here. Next. So here, first example, we're given 4 different types of equations, and our job is to identify which conic section we are talking about. So first one, I'm noticing that we have an x squared term and we have a y squared term. They're on the same side of the equal sign, right? And they're of opposite signs. So this is a hyperbola. Next, I have a y squared term, but I do not have an x squared term. This is a parabola. Next, I have an x squared term and a y squared term, and they are the exact same number, right? The coefficients, so the a and the c are exactly the same, leaving us with a circle for that one. And lastly, we have an x squared term and a y squared term, and their coefficients are of the same sign, which means it's going to be an ellipse. Now, if you had moved everything to the other side of the equal sign, they would both be positive. So they're either both positive or they're both negative to make the ellipse. Right. And notice none of these had a term that had an xy in it. So the b value was 0 for all of these. Okay. My notes for this section correspond with the OpenStax textbook. The OpenStax Precalculus textbook has some try it problems in it, so feel free to find this section. Try these problems and then you can check your answers there with the textbook. It's also an ebook. All right, so what happens when we have a b that is not 0? If you look in this example, you will notice we have a b. The b is a -1, but there is an xy term. So I cannot look at the x squared and the y squared and say, hey, it's a circle. Nope, can't do it. Can't do it because there's a b. So those rules only applied if the xy term didn't exist. Okay? So when we have a b term, like this one, it means that the conic section is not straight horizontal or straight vertical like we're used to seeing. It means that it's been rotated. Okay, so I have a little picture here in the corner. When we have a rotated conic section, we're going to rename our axes. So rather than using the x-axis and the y-axis, we're going to use an x prime axis and a y prime axis. Okay, and we'll have to use an angle to identify where that axis is. Okay, the x prime and the y prime axes are perpendicular to each other, but you know, how big of a slant, right, is this ellipse rotated? Well, that would be the theta. So we'll have to have we do have an example coming up where it discusses how do we find that theta, that angle at which we have rotated the conic section. So, all right, first things first here, this first example of this, they give us the theta. They're telling us that our conic section has been rotated 45 degrees. So I already know that it's not going to be straight. Well, that's not what I wanted. That it's not going to be a straight y-axis, x-axis. We're going to have a 45-degree rotation. So our axes are actually here, and that'll be x prime axes, and here with a y prime axis. Okay, so rather than using the original xy, we have a new xy, and you know, we label on it the same. Like so. Okay, so let's fill in some other information here and see if we can get the new representation for this conic section. Okay, now our goal is to maybe rewrite this so that we don't have an xy term in it, which means we're going to write it so that everything is x prime or y prime, because it will be graphed and plotted using the red axes that I have sketched here. So here's how we're going to do that. Right here, we are going to replace in the equation, we're going to replace the x's with x prime, now the cosine of 45 degrees, minus y prime sine of 45 degrees. Similarly, we're going to replace y with x prime sine of 45 degrees plus y prime cosine of 45 degrees. Now, we do know that the sine of 45 degrees is root 2 over 2. We also know that the cosine of 45 degrees is root 2 over 2. So that means that our x is going to get replaced with x prime root 2 over 2 minus y prime root 2 over 2. Okay, and very similarly, our y is going to look like x prime root 2 over 2 plus y prime root 2 over 2. Okay, so what does that mean for us? That means that I'm going to take this equation now, and I'm going to say 2x, and my x is, there's a couple different ways we could do this, right? I know x is all of this, so I'm going to put that into the x spot. I could factor out the root 2 over 2 first. You know, maybe. Let's see if I can do that. Root 2 over 2 factors out. of x prime minus y prime, but all of this is going to get squared. So I have a 2 in the front. If I square root 2 over 2, it's going to turn into a 2 over 4. And then x prime minus y prime. That is going to be squared still. So if I want to take it one more step, this is going to be 4 over 4. And this is going to be y prime squared. Remember, I'm writing this twice and then foiling it out. So I'll get a y prime squared. I'll have a x prime, y prime. I think I misspoke again. I meant x prime. Jeez Louise. All right. Because when you do your outer and your inner, you're going to get the same thing twice there. Okay. And then at the end, I'm going to have a plus y prime squared. Okay. That's just the 2x squared. Behind that, I have a minus x, which is root 2 over 2 times x prime y. X prime minus y prime times, that was just original x, right? I need to fill in now original y, which is root 2 over 2 times x prime plus y prime. Holy smokes. Well, there's a few things here I can clean up, right? Like I'm looking at these two, and that can make 2 over 4. And then when I FOIL these two, I'll get x prime squared. I'll get an x prime y prime minus an x prime y prime and a minus y prime squared. So that's what I would get when I FOIL that out. This can be simplified. So minus, so I'm just cleaning up this piece now, minus 1/2 x prime squared, right? I got a parenthesis here, so I'm distributing that minus sign also, right? And there. So the 1/2 is getting distributed and the minus sign. So this one will turn into a plus 1/2 y prime squared. Okay? Goodness gracious, that was just this piece. Now we're at plus 2y squared. Okay, well, what's y, right? 2y squared. Well, y, root 2 over 2 times x prime plus y prime. And that whole thing is getting squared. Well, if it's multiplication, I can break them apart and square each one of these separately. So, although there is a 2 in front, so I kind of have to be a little bit careful here, right? Root 2 over 2 squared is going to turn into a 2/4. The next piece, x prime plus y prime squared, is going to turn into an x prime squared plus, now if you're thinking about writing this twice and foiling it out, I'm going to get an x prime y prime 2 times. Once for the outer, once for the inner. And then a plus y prime squared. Whew. Now, my coefficient here is 4 over 4, so that's nice. And then I have a plus sign, so plus x prime squared plus 2x prime y prime plus y prime squared. Holy smokes, is it ugly? Now, I'll tell you a little trick. If you're doing this to try to rewrite your equation of an ellipse, or whatever. I guess I didn't say that was an ellipse just yet. Or any conic section. Your middle term, that the B term, should disappear, turn into 0. Reason is, that's why you're doing this work, right? So that we can write it in a form that we recognize. If it's in a form we recognize, we can graph it, we can identify the shape, all the things, pull out the ABC so we can plot it, okay? I do have a negative 2 x prime y prime and a plus 2 x prime y prime. So that is in our favor. That means so far so good. If that doesn't happen for you, you've made an error. So it's kind of a red flag to stop and go back. All right, so now let's combine like terms. I am seeing an x prime squared there, x prime squared there, x prime squared there. So 1 minus a half is a 1/2, plus another one, we'll have 3 halves. So we have 3 halves x prime squared. Looking at my y prime squareds, I have there, there, and there. Well, this is like, 2 halves of them. This is 1/2 of them, another 2 halves of them. So we have 5 halves y prime squared. Now, I lost my equal sign along the way here, so I need to be careful. Behind here, I have minus 30, minus 30, minus 30, a minus 30 equals 0. I'm going to add 30 to the other side because there's a minus. Add 30 to the other side. I can then divide everything by 30 to get a 1 right there. If you think back to conversations about ellipse and hyperbola, we need it to equal 1. We're not going to subtract 29 off. Okay, that's going to mess with us. Instead, we'll divide. So if we divide everything by 30, this will become 3x prime squared over 60 plus 5 y prime squared over 60 equals 1. I really like this because I can simplify it now. X prime squared over 20 plus y prime squared over, let's see, what do we get here? 10, 12 equals 1. I'm just simplifying the 5 over 60 and the 3 over 60, right? Okay, now I recognize this. I recognize this as an ellipse with the center at 0, 0, with the a value of root 20, with a b value of root 12. C, I have to do, think back to your ellipse section, right? We have a relationship. We solve for C, same way we did when we were on ellipse. It's going to be root 8. Okay? So here's what I know about this. Another thing to refresh your memory, a squared is equal to b squared plus c squared. That's how I got the c. A is the distance from the center to vertice. B is the distance from center to covertice. C is the distance from the center to the foci. Okay, so here's what I know. Remember, we weren't using the original x and y axis, right? We are using at a 45-degree rotation. This is our x-axis, so we called it x prime. And this is our y-axis, y prime. So our sketching and our graphing is going to be the same, but we're not doing it on the original X and Y axes. We're doing it on the X prime, Y prime axes. And it looks like this. From the center, which we know is 0, 0. 1, 2, 3, 4, 5. 1, 2, 3, 4, -5. Now, square root of 20 is more than 4, less than 5. So our vertex is here and here. Co-vertices is root 12 from the center. And remember, on an ellipse, that's just like your width the other way. So square root of 12 is about what's more than 3, less than 4, right? So 1, 2, 3, 4, 1, 2, 3, 4. So somewhere in here is where we have the B value. And then our foci, root 8 is more than 2, less than 3. In there. So foci, co-vertices. So my ellipse is elongated this way. Oop, come on, graph. There you go. And I'm not an artist, but there you have it. Okay. It wanted the equation without that middle X, Y term, and we have it. We just changed the axes. All right. Let's see what else.